Hello, dear students, welcome to today's class. In this video, we discuss reactions of carboxylic acids. We can divide reactions of carboxylic acid into two categories. The most important reactions include formation of acid derivatives, carboxylic acid derivatives, or we can call functional derivatives, and the second type are special reactions that we'll discuss in another video. Here we discuss only formation of acid derivatives. If you look into the mechanism, we can see that formation of acid derivatives from carboxylic acids are all coming under nucleophilic acyl substitution. That means some nucleophile will be attacking this carbonyl carbon, causing the replacement of OH group. So it's basically a substitution reaction, and that takes place at the acyl carbon. This is an acyl group. Now, in carboxylic acid, the reactions can be either loss of H plus. See, the reactive part of carboxylic acid is always OH, and the reactivity is due to the effect of this CO. OH can lose H plus, and that is the reaction with base that we discussed in the previous class. That's the acidity of carboxylic acid, and the other type is replacement of this OH. Loss of OH as a whole, replaced by some nucleophile. So, in general, if a nucleophile attack this carbon, OH get replaced and it is replaced by another group Z. Now this Z, the incoming group, can be 4. So there are 4 acid derivatives. If it is Cl, in general, if it is halogen, especially Cl, it is acid chloride. In general, acid halide. This can also be called acyl chloride. If it is NH2, then it is called acid amide. If it is OR, Z is OR, then it is ester. If it is OCOR, then it is acid anhydride. We will discuss each of these reactions in detail. Okay, look here. This is a summary, what we are going to discuss in detail. Carboxylic acid can be converted into acid chloride using any of these reagents. You may recall the reactions of alcohol where you learn the same reagents. Converting alcohol into alkyl halide, you can use any of these reagents. Then converting carboxylic acid into acid amide, you can heat with ammonia. To convert carboxylic acid into ester, you have to use an alcohol, right? And some dehydrating agents or in presence of acid which act as the catalyst. And finally, carboxylic acid get converted into acid anhydride by loss of H2O water by reacting with the same acid molecule or a different acid molecule by heating in presence of dehydrating agents like P2O5. In connection with esterification, this is called esterification, we have the term that's called Fischer Esterification, and we have the mechanism to discuss. And Planck's rule is related to this formation of acid anhydride by heating dicarboxylic acids. So we start with formation of acid chloride. Let me write RCOOH. You can use PCl3 or PCl5 or SOCl2, any of these reagents. the byproduct will be different. Always you get the same product, that is RCOCl, okay, plus. If it is PCl3, the byproduct will be H3PO3. If it is PCl5, it is the same product plus the byproducts are now POCl3 plus HCl. If it is thionyl chloride, and remember this is the best reagent for chlorination, thionyl chloride. Why? Because the byproducts formed SO2 and HCl, these are gases, so it can be easily removed from the product. And again, SOCl2 has low boiling point, so if there is excess reagent, that also can be easily distilled off. Taking a specific example, you try to write the product of this. Acetic acid is treated with thionyl chloride, write the product. Another example, benzoic acid is treated with thionyl chloride. What are the products? You can complete easily, isn't it? Simple, OH to be replaced by Cl in both cases, and write the byproduct also. Now, coming to the next one. See, when you learn the reaction, you should try to interpret it either in terms of mechanism, or at least you should know what is happening or how the reaction takes place. Like for example, see, this is react with SOCl2. It can be understood in this way. SOCl2 can be written like this. SOCl2. Okay, you write like this the reagent, and you can understand what is happening like this. See, so this is the product, SO2 and HCl. So that will leave a mental picture of the reaction, and a reaction can be interpreted in this way. Wherever mechanism is explicitly mentioned, you should go into the detailed mechanism. Coming to the next one, the second one, formation of acid amide, treating with ammonia, heating with ammonia. Let's write the general reaction. Acid is treated with ammonia. See, ammonia is a base. So initially it forms a salt, correct? Because this is acid, this is base. So what is formed first? It forms RCOONH4 plus, that is ammonium carboxylate. You get a salt, which on heating lose water minus H2O. It will lose water and form RCONH2, that is acid amide. Okay, this reaction involves two steps. So generally what is done is, for convenience, acid is first converted into acid halide. See, remember a point that among the 4 acid derivatives, this is most reactive acid derivative. So, to prepare these derivatives, generally what is done is, acid is first converted into acid halide, which is more reactive than acid itself, and then converted into this conveniently. So here you see, this become RCOCl. Now this can easily react with ammonia, forming the product in one step. You get amide. Because this is now, reaction is quite easy. We can write this NH3 as HNH2 and HCl is lost. Here HCl is a byproduct. Okay, you can write a specific example. What is the reaction between acetic acid treated with ammonia and heated? Predict the product. Very simple. You can easily write. You will be getting acid amide And what is the byproduct here? If it is carboxylic acid, it will be water. Okay. Now coming to the third one. So you have to practice reactions writing like this. Coming to the third one. That is carboxylic acid reacting with alcohol forming ester. This is a very, very common reaction, you know this. And this reaction is an analytical test for both alcohol as well as carboxylic acid in organic analysis. So carboxylic acid reacting with alcohol in presence of a dehydrating agent like anhydride zinc chloride can be used, or concentrated sulfuric acid, or even dry HCl. You can have acid catalyst, okay, or you can even use anhydride zinc chloride, some dehydrating agent. Let's see the reaction. Carboxylic acid react with alcohol. Let me write alcohol the other way. Just to differentiate, this is R dash, alkyl part of the alcohol. In presence of, say for example, HCl or H2SO4 or an acid, what happens? This is what's happening. See, what's the product? You get RCOOR dash plus H2O. An important point regarding esterification, this reaction is called esterification, formation of ester. An important aspect of this reaction is that this is reversible. It's a reversible reaction. Okay, and so it comes to an equilibrium. So to shift equilibrium to the right to get more product, you have to apply a Lee-Scheidel principle. Generally, we use more excess of alcohol, or whichever is cheaper is taken in excess. And another method is removing water. That's why we use some dehydrating agents. So water is removed, equilibrium will be pushed to the right. Okay. Now for esterification you can use, this is alcohol, you can as well use phenol, isn't it? Phenol also will undergo esterification. But the point is that phenol reacts slower than alcohol. So there's an intelligent question to you, why? Why phenol is slower in esterification than alcohol? Question is left to you. Now, what is, in this connection we have what is called Fischer Esterification and its mechanism. What is Fischer Esterification? It's simple, the same thing. Formation of ester by treating carboxylic acid with alcohol in presence of acid catalyst. No other dehydrating agent. If you are using acid catalyst, then it is known as Fischer esterification. So acid catalyzed esterification is Fischer esterification, right? Okay, we have the mechanism. Okay, before that, I am giving a specific example to you for practice. I am writing here, benzoic acid is treated with methanol in presence of acid. What is the product? You get ester. And what is the ester? What is the name? Okay, write the product yourself. What do you get? You can easily get, you get ester. This OH is replaced by this alcohol part, so it will be OCH3. What is the name of this ester? See, naming of acid derivatives we will discuss in another section. Anyway, here this is methyl benzoate, correct? Methyl benzoate plus H2O. Now, this is reversible because, the reaction is reversible because this H plus can cause the reverse reaction. See, it's notable. The forward reaction is called esterification, right? Catalyzed by H plus. And what is the reverse reaction called? Ester is broken into acid and alcohol using water. That is known as ester hydrolysis. Interestingly, both reactions are catalyzed by the same thing, that is H plus. That's why it is highly reversible. Okay. Now we'll go to the mechanism, Fischer mechanism. Okay, mechanism of Fischer esterification. See, the reaction is this: acid react with alcohol in presence of acid forming ester. Reaction takes place mainly in two steps. The first step is addition of this. See, I told you these are all nucleophilic acid substitution as far as mechanism is concerned. So the nucleophile here is alcohol. You know, nucleophile is anything which has a lone pair. So it looks for electron deficient center. So nucleophile is added to this acid. That is the first step. And the second step is loss of the leaving group. OH is removed as H2O, not as OH, as water. So nucleophilic addition, that is the first step. Addition of nucleophile. We can name it, we can remember the mechanism in terms of the steps. So first step is addition of nucleophile. What is the nucleophile here? That is alcohol. Okay. Now look at the mechanism. See, before nucleophile comes, what is the role of acid here? It is a catalyst. Actually, what is happening is this acid get protonated on this carbonyl group. Okay, so let us take the acid is HA, for example. If it's HCl, HA in general, what happens? This I can write in like this. HA can be shown like this. So we know H plus is attached to this oxygen, so that the protonation takes place, and this conjugate base is split apart. So what do you get? This become double bond OH, and of course a positive charge appear here, formal charge, because the lone pair is used for bonding, and then you have OH here, this OH plus A minus is removed. Okay, that will appear later. Now what happens? This is reversible, of course. What happens now is that comes the nucleophile. What is the nucleophile? Alcohol. So let me write alcohol here. So alcohol now attacks at this carbon. So actually this acid is making this carbon more positive, because when it is protonated there is a positive charge here, so this will now more easily shift. That is the role of acid as catalyst in all such reactions of carboxylic acids. So this attack, and now it becomes, this becomes OH, positive charge is gone, okay, and like this. Now positive charge appear here because this lone pair is used, and now comes this of course, you know, we have this A minus here, the conjugate base, which comes now here, A minus, and it will cause loss of this proton. Okay, so it will abstract this proton here, and you get this intermediate product, that is RCOH, OH and OR. This is the intermediate product obtained. This is not the end product. Now in the second step, so this is the first step, addition of nucleophile. What is the second step? Now you have to see, when this OR comes, OH has to go. So loss of this leaving group. An interesting thing is that here, see, acid acts as a catalyst, H plus is used up here, and it is now, see, this H plus is removed or lost. So HA is used up in one step and regenerated in the last, in another step. That means it's a catalyst. Now coming to the second step, loss of leaving group. loss of leaving group, that is, remember, leaving group is H2O, not OH. You know, in nucleophilic substitution reactions, you might have learned about the tendency of leaving group, reactivity of nucleophile, etc., where H2O is a better leaving group than OH minus. So again, it is the acid which plays the role. Actually, this can be easily taken like this. This is a geminal diode, correct? Two OH on the same carbon, it is unstable. It will simply lose water and you get the product. This is the ester. This becomes double bond. But mechanism wise, what is happening is like this. So let me go to the second part of the mechanism. See, this is not two-step reaction. Actually, this is one part of the mechanism which involves a few steps. And the second part of the mechanism is loss of leaving group like this. So let me write what is the OH and OR. Okay, what happens is, again comes this acid molecule, right? HA comes here, and it now it is this OH get protonated. See, whenever there is lone pair, H plus can attach. So this OH get protonated, this break away. So what do you get? What do you get? It becomes now R OH and positive charge here, and this OH is there. Okay. Then OR here. Let me show this OH clearly. Plus A minus is removed here. Now this will go. This is now the better leaving group. OH is not a good leaving group. So protonation make it a better leaving group, because now this easily breaks. Correct? This can easily break. Assisted by this lone pair. Okay? So what do you get now? Let me write it here now. What do you get now? This now become, this is now becoming double bond OH, now positive charge is here, and that is lost there, and it is now OR here. Water is lost. Okay, plus H2O. Water is the byproduct, of course. Then now comes A minus back. The conjugate base of the acid, it can now abstract this proton. That's the final step. You get the product now. What is now the product? This become now RC double bond OOR plus HA. Again, in this second part also, illustrating that acid is a catalyst, used up in one step, regenerated in the other step. This is what is Fischer mechanism. Okay, so it's very interesting to practice this mechanism so that you understand reactions very close and you will never forget it. Okay, now finally we have the last one, that is formation of acid anhydride from carboxylic acid by heating. See, if you take carboxylic acid and you simply heat it in presence of a dehydrating agents like P2O5, the same molecule can undergo, two molecules of the same acid can undergo dehydration like this, and this water is taken up by this P2O5 dehydrating agent, and what you get? You get the product RCOO COR. What is this called? This is called acid anhydride because it has lost water. That's why anhydride. Correct? Now if you are using two different acids, suppose, see, this is called symmetric anhydride because the two R groups are identical. If you are using this acid and another acid R-COOH, it is interesting. heated in presence of P2O5. What about anhydrides? How many anhydrides you get? You get 3 different anhydrides. That is, 2 molecules of this acid can undergo dehydration getting this. 2 molecules of this acid, because there are so many molecules, right? You get another anhydride that is from this one, and it can be 1 molecule of this and 1 molecule of this can undergo dehydration giving another anhydride, which is a mixed anhydride. So the products are anhydride can be simply written like this, RCO twice O. You understand? Because see, this is like there are RCO 2 times O plus this. From this acid you get what? R dash CO twice O plus between these two what you get? It will be RCO O COR dash. This is an unsymmetrical or mixed anhydride. These two are symmetrical anhydrides. Okay. Now finally, if you take dicarboxylic acids, see, another point is, for preparing anhydride, there is an easier method will be, you convert acid first into acid halide, okay, using thionyl chloride, and then you treat with acid will be better. Why? Because then it is HCl and you can use bases like pyridine here. Okay. So what happens? HCl, this is what happens. You will be getting anhydride RCO twice O more easily, more quickly, because this is more reactive, and HCl form will be removed by the base used. Okay. Now, in the case of dicarboxylic acid, there is a rule called Blanc's rule. What is Blanc's rule? See, if you use a dicarboxylic acids, for example, let me write oxalic acid. Okay, oxalic acid is used. You heat it in presence of dehydrating agents like acetic anhydride, for example. What happens? What happens here is, here we expect a cyclic anhydride, but it's not stable. In this case, carbon dioxide will be lost and it reduces to a monocarboxylic acid, that is HCOOH plus CO2. This is what you get. You won't get anhydride. So Blanc's rule says that the generalization is this. If you go to the next member, that is CH2CO, this one. What is this compound? We have discussed this one, dicarboxylic acid. What is this? The next homologue. This is called malonic acid. Here also, this is not what is formed, not a cyclic anhydride. It is unstable. Here also the same thing happened, that is, on heating, carbon dioxide is lost, decarboxylation takes place, and it become what? H will be added here and it become CH3COOH. That means it reduces to monocarboxylic acid. But the anhydrides are obtained from the next member onwards. So in general, we can write that Blanc's rule can be generally written like this: CH2N times COOH COOH. Okay. If N is equal to 0 or 1, if it is N equals 0 or 1, that means if 0 means it is oxalic acid, 1 means malonic acid. In that case, the product is a monocarboxylic acid. You get monocarboxylic acid by loss of CO2. We discussed that. If it is 2 or 3, that means if it is 0, you can call it 1,2 dicarboxylic acid according to APC rule. If it is N equal 1 means malonic acid, then we can call it 1,3 acid. If it is 2, that is succinic acid. That means COOH, CH2, CH2COH. If it is 3, that is glutaric acid. Then there are 3 CH2 here. In these two cases, you get anhydride. You get cyclic anhydride. We can put an example. Let us take succinic acid for example. This is succinic acid. On heating this lose water like this, form cyclic anhydride, which will be like this. You can be conveniently drawn like this. This is succinic anhydride, okay? Because this is a stable ring. And it can go to 6-membered ring also. That means if you take glutaric acid, one more CH2 in between, you get glutaric anhydride. But Blank's rule says that when the ring size increases to 7 or 8, it is unstable. That means if n equal 4 or 5, what happens is that, for example, let us take, if it is 4, that means adipic acid, okay? It can be drawn like this, adipic acid. There are 4 CH2 groups here, you know this adipic acid. This on heating, we may expect formation of anhydride, okay? It's not anhydride because that will lead to a 7-membered ring system which is not so stable. So water will be lost and the CO2 also will be lost. So here there is minus H2O, dehydration, as well as decarboxylation. See, it's interesting. In this case, it is losing CO2, that is decarboxylation, forming monocarboxylic acid. In this case, it is losing water, forming the expected product, that is anhydride. In this case, it loses both H2 as well as CO2. So the product will be now like this. It will be like this. What is this product obtained? What is this product obtained? It will be a cyclic ketone. See, it's a cyclic ketone because CO2 is also lost. What is this? Cyclopentanone, isn't it? Cyclopentanone. Okay? So that is Blank's rule. If it is 5, this is actually 1,6 dicarboxylic acid. If it is 5 means it is 1,7 dicarboxylic acid. That will be giving cyclohexanone. So that is what is Blank's rule. Now finally, an interesting example of this unsaturated dicarboxylic acid, that is the cis-trans isomers. See, you name this compound. What is this compound? This is exhibiting cis-trans or geometrical isomerism. This is a cis isomer. What is this? You know, this is called malic acid. Okay, not malic, that is different. This is malic acid. Its trans isomer is this one, changing the side of carboxylic acid. This is, what is this called? The trans isomer of malic acid. This is called fumaric acid. Now this example illustrates how interestingly we can make use of the ease of anhydride formation to distinguish the compound. How you distinguish these two compounds? Very simple. You just heat this malic acid, it easily undergo dehydration and forming anhydride. You get malic anhydride, that is, you get like this. This is called malic anhydride. You can heat it only at 150 degrees, that's enough. 150 degrees Celsius, you get the product. But fumaric acid, it will not undergo cyclization or dehydration easily because the two COHs are on opposite side. So this is easily converted into anhydride, this is not. However, if it is heated very strongly, it can isomerize into this at 250 degrees Celsius. It does undergo anhydride formation, but it is difficult. So that is okay. So that's all about formation of acid derivatives from carboxylic acid, and the other reactions we'll discuss in the next class. Till then, bye.